Good morning, students. We'll continue again with our unit number 3, which is design of industrial building. So the first topic is column and beam structures. Column and beam structures, it requires an independent bracing system. And this bracing system should be in both the directions. So the beams may be I sections or lattice trusses. Column and beam structures with hinge column bases. For simple beam and column structures, the columns are loaded mainly in compression, and this leads to smaller columns. So compared to a portal frame, the internal moments in the beam are greater, and this leads to larger steel sections. So since pinned connections are less complex than moment resisting connections, fabrication costs can be reduced. Table 3.2 gives some indicative column and beam sizes for a hinge column base. For this type of support structure, bracings in both directions are required in the roof as well as in the walls in order to provide stability for horizontal loads. For that reason, it is often used for predominantly enclosed halls, that is, no substantial openings or no openings at all. So this fact also has to be taken into account during the installation stage by providing temporary bracings. This is your table 3.2 with the pre-designed table for column and beam structure showing snow load, span, height, pitch, frame spacing, required cross-section in column and beam. This is figure 23, which is a coal-formed sections typically used for purlins. Z shape, C shape, and U shape. Column and beam structures with fixed column bases. So when using fixed-ended columns, larger foundations are required as a result of the additional bending moment. As the columns have low axial forces, the required size of the foundation will be large and possibly uneconomic. So large columns for industrial buildings with a crane may be designed as lattice structures. Compared to portal frames, internal moments in the beams and lateral deformations are greater. So the advantages of this system are its insensitivity to settlement, and in the case of the fixed supports, the base stiffness acts in both directions and the structure is stable after installation without additional bracing. Secondary components and bracing. A typical steel portal frame structure with its secondary components is shown in figure 24. Similar systems are provided for beam and column splices. The bracing systems shown in figure 3.1 are generally achieved by bracing, usually circular members, in the plane of the roof or wall. Purlins and side rails support the roof and wall cladding and stabilize the steel framework against lateral buckling. Alternatively, panels providing shear stiffness or steel profile sheeting used in diaphragm action can be used to provide sufficient out-of-plane stability. So this is the picture showing cross-section portal frame and its restraints having foundation, column, base plate, haunch, rafter, again haunch, purlins, positions of restraint to inner flange of column and rafter, tie rod that is optional but it is not common, then wall, side rails, and cold roll eaves beam. Next one is roof steelwork plan having plan bracing, cold roll purlins, sag bags if necessary or if required, cold roll eaves beam and eaves beam strut. That is strut. Next is side elevation having sidewall bracing, sag rod, side rails, and diagonal ties. Overall, this is an overview of secondary structural components in a portal frame structure. Next is connections. The three major connections in a single bay portal frame are those at the edges, the apex, and the column base. For the edges, bolted connections are mostly used of the form as shown in figure 25. A haunch that can be created by welding or cutting to the rafter in order to increase its depth. The depth is increased locally and to make the connection design more efficient. The cutting is often made from the same steel section as the rafter. In some cases, the column and the haunches part of the beam are constructed as one unit and the constant depth part of the beam is bolted using an end plate connection. So in order to reduce manufacturing costs, it is preferable to design the edges connection without the use of stiffener. So in some cases, the effects of the reduced joint stiffness on the global structural behavior may have to be considered, that is, the side effects of the internal forces and deflections. Next, the apex connection is often designed similarly. So if the span of the frame does not exceed transportation limits, which is about 16 meter, the on-side apex connection can be avoided, thus saving cost. The base of the column is often kept simple with larger tolerances in order to facilitate the interface between the concrete and steelwork. So pin connections are often preferred in order to minimize foundation sizes. Although stability during construction must also be considered. So high horizontal forces may require the use of fixed base connections. These are typical apex connections in a portal frame. And this is a typical example of nominally pinned column bases in a portal frame. You can give your attendance now in the chat box. Thank you.